Hello, this is the final presentation for PKO Flaherty, Classify Abalone by KNN. Can we classify abalone as male, female, or sexually immature based on length, weight, and age? I got this data from the UCI Machine Learning Repository, the abalone dataset, and normally this data is used to predict age based on the available data. That problem's been done, so I wanted to identify male, female, or infant from the available data. If you look on the far right, those values for length and weight are very small. They've all been divided by 200 for scaling to be fed into a neural network. And for rings, let's say there's 9 rings, that represents 10 layers of shell for 10 years of life, plus 6 months for a juvenile stage. Normally we would do exploratory data analysis. We did that in the proposal and identified that the lengths and weights for males, females, and infants overlap greatly, and so it's going to be a difficult problem. We wanted to extend that exploratory data analysis by looking at average growth in length and average growth in weight per year. So in the data wrangling, we are adding column names, undoing that scaling by multiplying those continuous values by 200, creating an age column by adding 1.5 to the number of rings, and then creating that average growth in length and average growth in weight per year by dividing length and whole weight by the age that we just calculated. For the exploratory analysis, in this graph we are only really able to compare length. This is a bar chart, and so each column is a series of stacked values for individual abalone. But what we can see is that the length for males and females largely overlap, and the length for infants even overlap quite a bit. Looking at that same data, but faceted by male, female, and infant, we show that the males and females have a very similar pattern of distribution. Maybe some males are able to sexually mature at shorter lengths than the females. And the infants, there are no infants over a certain length, it seems, but it's notable that at any given length, the infants tend to weigh less. So this could mean two things. Maybe the infants don't have sperm or eggs that could be contributing to total body weight, or if sexual maturity isn't triggered by reaching a certain age or reaching a certain length, then maybe it's triggered by food availability. And so these older infants that still haven't sexually matured, maybe they just aren't in an environment where they're able to grow enough that they could focus on reproduction. Here we look at average growth in length per year, and we don't really see differences. However, when we look at average growth in weight per year, we do see that difference where the infants aren't growing as much in weight. So for the machine learning section of the project, I'm going to go through it step by step. We're splitting the data between X and Y, and note that the Y being the target, male, female, and infant, and X being the remaining columns. However, we're not using the 3 columns that we created from the others. Since they're created entirely from the other data, they have no new data and aren't of value to the model, even if they were of value to us in identifying what to look for. Then we split the data into training and test. And here I got this wrong in a discussion on Slack, but fit transform, you're normalizing the X-train data, and it remembers that mean and variance in order to get the training data to have a mean of 0 and a standard deviation of 1. When we then later transform the test data, we're not normalizing it because we're using the mean and variance from the training data in order to mostly normalize it, to transform it into being close to 0 mean and close to 1 standard deviation. The distinction is subtle, but the purpose is for consistency. Any number of tests that test data that you run they're going to be transformed the same way. Say you get new data and you only have 3 new records that you need to model. It could be that the mean and variance are off, so you want to use that mean and variance from the training data. Here we instantiate an object of the class k nearest neighbors with 5 as the number of neighbors, and we fit that model to the X-train data. And here we predict values for the test data using that model. And now we compare it to the actual Y values for the test data, and we get an accuracy of 55%. This isn't great. True guessing would be 33% since there's 3 of them. And from everything we've observed so far, we're guessing that we're having a hard time distinguishing between males and females, but we can distinguish between infants and non-infants. So we're going to look at that next. We recreate those steps. However, now we've removed all of the infant records, and we get an accuracy of 54%, which is a significant reduction in success from the previous example because there's only 2, male and female, and true guessing would be 50%. Here is repeating the general case, but only looking at infant or not infant. We set the male and female variable values to mature, and we get an accuracy of 82%. So we can conclude that all of our success in the general case was our ability to identify infants and not from our ability to distinguish between males and females. Before we move away from this, I wanted to look at how different values of number of neighbors could influence the results. In the special case of nearest neighbors equal to 1, we get the definition of overfitting, where we have 100% training accuracy and a low testing accuracy. Now, we never see the opposite of overfitting, underfitting. Maybe if we had a much higher number of neighbors, we would show testing and training accuracy both drop. But given the ranges we did look at, it looks like you would want to use a number of neighbors between 25 and 30. So we weren't able to reliably identify between males and females, maybe in the extreme case when they're very small. And we only could partially identify infants versus non-infants. It may be that the males and females have, or abalone have low sexual dimorphism, where the males and females are roughly the same size and shape. And for sexual maturation, it seems like age or length alone doesn't seem to be a trigger. So it could be if they're able to get enough food, something outside of the scope of what we measured in the data. If someone were to extend this presentation, they could try the classification using a different model, maybe logistic regression or a neural network, or they could pick a different column as the target variable, such as weight and age, and try linear regression or a neural network. I've learned a lot about Abalone and machine learning, specifically the difference between fit transform and transform, and also a lot about formatting IP, Y, and G files for rendering the graphics in browser or HTML or PDF. So if you have any questions about that, feel free to ask me. This concludes the presentation. Thank you.